Introduction to Groups. In this video, we are going to see about Introduction to Groups. Groups, rings, and fields are the basic elements of a division of mathematics known as abstract algebra or modern algebra. In abstract algebra, user can combine two elements of the set and perhaps in several ways to obtain a third element of the set. It is significant to note that in abstract algebra, the user is not limited to ordinary arithmetical operations. Groups. A group G, sometimes represented by G, dot, where the operator dot is generic and can refer to addition, multiplication, or some other mathematical operation. It is a set of elements with a binary operation represented by dot that associates to each ordered pair A dot B of elements in G an element A dot B in G such that the following axioms are obeyed. A1. Closure. If A and B belong to G, then A dot B is also in G. A2. Associative. A dot B dot C is equal to A dot B dot C for all A, B, C in G. A3. Identity element. There is an element E in G such that A dot E is equal to E dot A is equal to A for all A in G. A4. Inverse element. For each A in G, there is an element A dash in G such that A dot A dash is equal to A dash dot A is equal to E. Let n subscript n represent a set of n separate symbols, that is, for expediency, we represent as 1, 2 and so on up to n. A permutation of n distinct symbols is a one-to-one mapping from nn to nn power 5. Define Sn to be the set of all permutations of n distinct symbols. Each element of Sn is represented by a permutation of the integers pi in 1, 2 and so on up to n. It is easy to demonstrate that Sn is a group. A1. If pi rho belongs to Sn, then the composite mapping pi dot rho is formed by permuting the elements of rho according to the permutation pi. For example, set 321 dot set 132 is equal to set 231. Clearly, pi dot rho belongs to Sn. A2. The composition of mappings is also easily seen to be associative. A3. The identity mapping is a permutation that does not alter the order of the n elements. For Sn, the identity element is set 1, 2 and so on up to n. A4. For any phi belongs to Sn, the mapping that undoes the permutation defined by pi is the inverse element for pi. There will always be such an inverse example. Set 231 dot set 312 is equal to set 123. If a group have a finite number of elements, it is referred to as a finite group and the order of the group is equal to the number of elements in the group. Otherwise, the group is an infinite group. Group is referred to be abelian if it satisfies the following additional condition. A5. Commutative. A dot B is equal to B dot A for all A, B in G. The set of integers positive, negative and 0 under addition is an abelian group. The set of non-zero real numbers under multiplication is an abelian group. The set Sn from the preceding example is a group, but not an abelian group for n is greater than 2. When the group operation is addition, the identity element is 0. The inverse element of A is minus A, and subtraction is defined by the following rule: A minus B is equal to A plus of minus B. Cyclic group. We describe exponentiation in a group as frequent application of the group operator so that A cube is equal to A dot A dot A. We define A power 0 is equal to E as the identity element and A power minus n is equal to A dash power n, where A dash is the inverse element of A in the group. Group G is cyclic if every element of G is a power A power k. K is an integer of a fixed element A belongs to G. Element A is said to generate the group G or to be a generator of G. A cyclic group is always abelian and might be finite or infinite. Introduction to rings. In this video, we are going to see about introduction to rings. Rings. A ring R, sometimes represented by set R, addition, multiplication, is a set of elements with two binary operations called addition and multiplication, such that for all A, B, C in R, the following axioms are obeyed. A1 to A5. R is an abelian group with respect to addition, that is, R satisfies axioms A1 through A5. We represent the identity element as 0 and the inverse of A as minus A. M1. Closure under multiplication. If A and B belong to R, then AB is also in R. M2. Associativity of multiplication. A into BC is equal to AB into C for all A, B, C in R. M3. Distributive loss. A into B plus C is equal to AB plus AC for all A, B, C in R. A plus B into C is equal to AC plus BC for all A, B, C in R. A ring is a set. In this, we can perform addition, subtraction. A minus B is equal to A plus of minus B and multiplication without exiting the set. With respect to addition and multiplication, the set of all square matrices over the real numbers is a ring. A ring is said to be commutative if it satisfies the following additional condition. M4. Commutativity of multiplication. A into B is equal to B into A for all A, B in R. Let S be the set of even integers positive, negative and 0 under the usual operations of addition and multiplication. S is a commutative ring. The set of all n square matrices defined in the preceding example is not a commutative ring. The set Zn of integers 0, 1 and so on up to n-1 together with the arithmetic operations modulo n is a commutative ring. We describe an integral domain. It is a commutative ring that obeys the following axioms. M5. Multiplicative identity. There is an element 1 in R such that A into 1 is equal to 1 into A is equal to A for all A in R. M6. No zero divisors. If A, B in R and A into B is equal to 0, then either A is equal to 0 or B is equal to 0. Let S be the set of integers, positive, negative and 0 under the usual operations of addition and multiplication. S is an integral domain. Introduction to fields. In this video, we are going to see about introduction to fields. Fields. A field F, sometimes denoted by set F, addition, multiplication, is a set of elements with two binary operations called addition and multiplication, such that for all A, B, C in F, the following axioms are obeyed. A1 to M6. F is an integral domain, that is, F satisfies axioms A1 through A5 and M1 through M6. M7. Multiplicative inverse. For each A in F except 0, there is an element A inverse in F such that A into A inverse is equal to A inverse into A is equal to 1. A field is a set which we can perform addition, subtraction, multiplication and division without exiting the set. Division is defined with the following rule. A by B is equal to A into B inverse. Familiar examples of fields are the rational numbers, the real numbers, and the complex numbers. Note that the set of all integers is not a field because not every element of the set has a multiplicative inverse. In fact, only the elements 1 and -1 have multiplicative inverses in their integers. This image explains overall concept of the fields. Introduction to integer arithmetic. In this video, we are going to see about Introduction to integer arithmetic. In integer arithmetic, we use a set and a few operations. We are well known with this set and the corresponding operations, but they are reviewed here to create a background for modular arithmetic. Integer arithmetic operations are set of integers, binary operations, linear Diophantine equations, integer division, divisibility. Set of integers. Set of integers represented by Z holds all integer numbers with no fraction from -infinity to +infinity. The set of integers can be constructed from the natural numbers. We can define the set of integers as the set n cross n, where cross is the Cartesian product. In set theory, the Cartesian product is the combination of all the elements of one set with all the elements of the other set formed in pair. Binary operations. In this video, we are going to see about binary operations. In cryptography, we are interested in 3 binary operations applied to the set of integers. A binary operation takes 2 inputs and creates 1 output. The common binary operations are addition, subtraction, and multiplication. These operations takes 2 inputs A and B and produce 1 output C. Example for the binary operations. The following shows the result of the 3 binary operations on 2 integers. Because each input can be either positive or negative, we can have 4 cases for each operation. Integer division. In this video, we are going to see about integer division. In integer arithmetic, if we divide A by n, we can get Q and R. The association between these 4 integers can be shown as A is equal to Q into n. In this relation, A is called the dividend, Q the quotient, n the divisor, and R the remainder. This is not an operation because the result of dividing A by n is 2 integers Q and R. It is called as division relation. Example, assume that A is equal to 255 and n is equal to 11. We can find Q is equal to 23 and R is equal to 2 using division algorithm. 2 restrictions. We impose 2 limits when we use the division relationship in cryptography. First, we need the divisor to be a positive integer, which is n is greater than 0. Second, we need the remainder be a non-negative integer, that is, r is greater than or equal to 0. The relationship with the mentioned restrictions. example, when we use a computer or calculator, R and Q are negative when A is negative. How can we apply the restriction that R needs to be positive? The solution is simple. We decrement the value of Q by 1 and we add the value of N to R to make it positive. Minus 255 is equal to minus 23 into 11 plus of minus 2. Minus 255 is equal to minus 24 into 11 plus 9. We have decremented minus 23 to become minus 24 and added 11 to minus 2 to make it 9. The above relation is still valid. The graph of the relation. We can represent the relation with two limitations on N and R using two graphs. The first one represents a case when A is positive, the second when A is negative. Starting from 0, the graph demonstrates how we can obtain the point representing the integer A in the line. In case of positive A, we need to move Q into N units to the right and then move extra R units in the same directions. In case of negative A, we need to move Q minus 1 into N units to the left and then move R units in the opposite direction. In both the cases, the value of R is positive. Divisibility. In this video, we are going to see about divisibility. Let us briefly discuss divisibility. This often occurred in cryptography. If A is not 0 and we let R is equal to 0 in the division relation, we get A is equal to Q into N. We then say that N divides A or N is a divisor of A. We can also say that A is divisible by N. When we are not interested in the value of Q, we can write the above relationship as A by N. Example, the integer 4 divides the integer 32 because 32 is equal to 8 into 4. If the remainder is not 0, then N does not divide A and we can write the relationship as A into N. Example, the number 8 does not divide the number 42 because 42 is equal to 5 into 8 plus 2. There is a remainder, the number 2 in the equation. We show this as 8 into 42. Properties. Following are several properties of divisibility. Property 1. If A is divided by 1, then A is equal to plus or minus 1. Property 2. If A is divided by B and B is divided by A, then A is equal to plus or minus B. Property 3. If A is divided by B and B is divided by C, then A is divided by C. Property 4. If A is divided by B and A is divided by C, then A is divided by M into B plus N into C, where M and N are arbitrary integers. All divisors. A positive integer can have more than one divisor. For example, the integer 32 has 6 divisors: 1, 2, 4, 8, 16 and 32. We can mention two interesting facts about divisors of positive integers. Fact 1. The integer 1 has only one divisor itself. Fact 2. Any positive integer has at least two divisors, one and itself, but it can have more. Greatest common divisor GCD. Greatest common divisor of two positive integers frequently wanted in cryptography. Two positive integers might contain common divisors but only one greatest common divisor. For example, the common divisors of 12 and 140 are 1, 2 and 4. However, the greatest common divisor is 4. The greatest common divisor of two positive integers is the largest integer that can divide both integers. Euclidean Algorithm. When the two integers are large, it is not practical to find the greatest common divisor GCD of two positive integers by listing all common divisors. Fortunately, more than 2000 years before, a mathematician named Euclid developed an algorithm that can find the greatest common divisor of two positive integers. The Euclidean algorithm is based on the following two facts. Fact 1. GCD A0 is equal to A. Fact 2. GCD of AB is equal to GCD of BR, where R is the remainder of dividing A by B. The first fact informs us that if the second integer is 0, the greatest common divisor is the first one. The second fact agrees as to change the value of AB until B becomes 0. We utilize two variables R1 and R2 to hold the varying values during the process of reduction. They are initialized to A and B. In every step, we compute the remainder R1 divided by R2 and accumulate the result in the variable R. Then substitute R1 by R2 and R2 by R. These steps are continued until R2 becomes 0. At this instant, we stop. The GCD of AB is R1. When GCD of AB is equal to 1, we say that A and B are relatively prime. For example, find the greatest common divisor of 2740 and 1760. Solution. We have GCD of 2740, 1760 is equal to 20. The extended Euclidean algorithm. Given two integers a and b, we often need to find other two integers s and t such that s into a plus t into b is equal to GCD of ab. The extended Euclidean algorithm can calculate the GCD of ab and at the same time calculate the value of s and t. The extended Euclidean algorithm uses the same number of steps as the Euclidean algorithm. However, in every step, we exercise 3 sets of calculations and exchanges instead of 1. The algorithm uses 3 sets of variables R-S, S-S, and T-S. In every step, R1, R2, and R contains the identical values in the Euclidean algorithm. The variables S1 and S2 are initialized to 1 and 0 respectively. The variables R1 and R2 are initialized to the values of A and B respectively. The variables T1 and T2 are initialized to 0 and 1 respectively. The computation of R, S, and T are akin with one warning. Even though R is the remainder of dividing R1 by R2, there is no such bond between the other two sets. Only one quotient Q, it is computed as R1 by R2 and utilized for the other two computation. For example, given A is equal to 17 and B is equal to 0, find GCD of AB and the values of S and T. Solution. We get GCD of 17, 0 is equal to 17, S equal to 1 and T is equal to 0. Here, we require no computation for Q, R, and S. The first value of R2 meets our extension condition. We obtain GCD of 17, 0 is equal to 17, S is equal to 1, and T is equal to 0. These points out why we must initialize S1 to 1 and T1 to 0. The answers can be experienced as shown below. 1 into 17 plus 0 into 0 is equal to 17. Linear Diophantine equation. In this video, we are going to see about linear Diophantine equation. The important application of the extended Euclidean algorithm is to find the solution to the linear Diophantine equation of two variables. The equation of type ax plus by is equal to c. Here, we have to find the integer values for x and y to satisfy the equation. This type has either no solution or an infinite number of solutions. Let D is equal to GCD of AB. If D into C, then the equation has no solution. If D is divided by C, then we have an infinite number of solutions. One of them is called the particular, the rest general. A linear Diophantine equation of two variables is ax plus by is equal to c. Particular solution. If D is divided by C, a particular solution to the above equation can be found using the following steps. Decrease the equation to a1x plus b1y is equal to c1 by dividing both sides of the equation by D. This is possible because D divides a, b and c by the assumption. Solve for s and t in the relation a1s plus b1t is equal to 1 using the extended Euclidean algorithm. The particular solution can be found. Particular solution x naught equal to c divided by d into s and y naught is equal to c divided by d into t. General solutions. After finding the particular solution, the general solutions can be found. General solutions: x is equal to x naught plus k into b by d and y is equal to y naught minus k into a by d, where k is an integer. For example, find the particular and general solutions to the equation 21x plus 14y is equal to 35. Solution. We enclose D is equal to GCD of 7 is equal to 7. Since 7 is divided by 35, the equation have infinite number of solutions. We can divide both sides by 7 to find the equation 3x plus 2y is equal to 5. Using the extended Euclidean algorithm, we find s and t such as 3s plus 2t is equal to 1. We have s equal to 1 and t equal to minus 1. The solutions are particular x0 equal to 5 into 1 is equal to 5 and y0 equal to 5 into minus 1 is equal to minus 5, since 35 by 7 is equal to 5. General. X is equal to 5 plus k into 2 and y is equal to minus 5 minus k into 3, where k is equal to 0, 1, 2 and so on. Thus, the solutions are 5, minus 5, 7, minus 8, 9, minus 11. We simply analyze that each of these solutions satisfies the original equation. Introduction of modular arithmetic. In this video, we are going to see about introduction of modular arithmetic. The division relationship A is equal to Q into N plus R, conversed in the earlier part, have two inputs A and N and two outputs Q and R. In modular arithmetic, we are concerned in only one of the outputs, the remainder R. We don't mind about the quotient Q. In other words, we desire to know the value of R when we divide A by N. This means that we can alter the above relation into a binary operator with two inputs A and N and one output R. modular arithmetic concepts explained by the following topics: modular operator, set of residues, congruence, operations in Zn, inverses, addition and multiplication tables, different sets for addition and multiplication, two more sets. Modular operator. In this video, we are going to see about modular operator. The modulo operator is shown as mod. The second input n is called the modulus. The output r is called the residue. The division relation evaluate with the modulo operator. The modulo operator mod receive an integer a from the set z and a positive modulus n. The operators create a non-negative residue r. We can say a mod n is equal to r. Example: find the result of the following operations: a 27 mod 5, b 36 mod 12, c minus 18 mod 14. Solution: a. Dividing 27 by 5 results in r is equal to 2. b. Dividing 36 by 12 results in r is equal to 0. c. Dividing minus 18 by 14 results in r is equal to minus 4. After adding the modulus, r is equal to 10. Set of residues Zn. In this video, we are going to see about set of residues Zn. The outcome of the modulo operation with modulus n is always integer between 0 and n minus 1. In other words, outcome of a mod n is always non-negative integer less than n. We can say that the modulo operation produces a set which in modular arithmetic is referred to set of least residues modulo n or Zn. However, we require to remember that although we include only one set of integers z, we have infinite instances of the set of residues Zn, one for each value of n. The set is Zn and three cases: z2, z6 and z11. Congruence. In this video, we are going to see about congruence. In cryptography, we frequently used the idea of congruence instead of equality. Mapping from Z to Zn is not one-to-one. Infinite members of Z can map to one member of Zn. For example, the result of 2 mod 10 is equal to 2, 12 mod 10 is equal to 2, 22 mod 2 is equal to 2, and so on. In modular arithmetic, integers like 2, 12 and 22 are called congruent mod 10. To show that two integers are congruent, we use the congruence operator. We append the phrase mod n to the right side of the congruence to describe the value of modulus that makes the relationship valid. For example, we write 2 is congruent to 12 mod 10, 13 is congruent to 23 mod 10, 3 is congruent to 8 mod 5, 8 is congruent to 13 mod 5. The idea of congruence. We need to explain several points. Congruence operator seems like the equality operator, but there is dissimilarity. First, the equality operator maps a member of Z to itself. The congruence operator maps a member from Z to a member of Zn. Second, the equality operator is one-to-one. The congruence operator is many-to-one. The phrase mod n is included at the right-hand side of congruence operator is just an indication of the destination set Zn. We require to add this phrase to illustrate what modulus is used in the mapping. The symbol mod used here does not have the similar sense as the binary operator. In other words, the symbol mod in 12 mod 10 is an operator. The phrase mod 10 in 2 is congruent to 12 mod 10 means that the destination set is Z10. Residue classes. A residue class set A or AN is the set of integers congruent modulo n. In other words, it is a set of all integers such that x is equal to A mod n. For example, if n is equal to 5, we have 5 sets, set 0, 1, 2, 3, and 4. The integers in the set 0 are all reduced to 0 when we apply the modulo 5 operation on them. The integers in the set 1 are all reduced to 1 when we apply the modulo 5 operation, and so on. In each set, there is only one element called the least, that is non-negative residue. In the set 0, this element is 0. In the set 1, this element is 1, and so on. The set Zn is the set of all least residue modulo n. Circular notation. The concept of congruence can be better understood with the use of a circle. Just as we use a line to show the distribution of integers in Z, we can use a circle to show the distribution of integers in Zn. The comparison between the two integers 0 to n-1 are spaced uniformly around a circle. Positive and negative integers from Z are mapped to the circle so that there is a symmetry between them. Example: we use modular arithmetic in our daily life. For example, we use a clock to measure time. Our clock system uses modulo 12 arithmetic. However, instead of a 0, we use the number 12. So, our clock system starts with 0 or 12 and goes until 11. Operations in Zn. In this video, we are going to see about operations in Zn. There are 3 binary operations: addition, subtraction, and multiplication that talk about for the set Z and defined for the set Zn. The result need to be mapped to Zn using mod operator. Here, 2 set of operations are used. First set is one of the binary operator, addition, subtraction, multiplication. Second is the mod operator. We need to use parentheses to emphasize the order of operations. The inputs A and B can be the members of Zn or Z. For example, perform the following operations. The inputs come from Zn. Add 7 to 14 in Z15. Solution: 14 plus 7 mod 15 implies 21 mod 25 is equal to 6. Subtract 11 from 7 in Z13. 7 minus 11 mod 13 implies minus 4 mod 13 is equal to 9. Multiply 11 by 7 in Z20. 7 into 11 mod 20 implies 77 mod 20 is equal to 17. Properties. We talked about that 2 inputs to the binary operations in the modular arithmetic can come from Z or Zn. The following properties permit us to first map the 2 inputs to Zn before applying the 3 operations: addition, subtraction, multiplication. First property: A plus B mod n is equal to A mod n plus B mod n into mod n. Second property: A minus B mod n is equal to A mod n minus B mod n into mod n. Third property: A into B mod n is equal to A mod n into B mod n into mod n. The process before and after applying the properties. The figure illustrates the process is longer if we apply the properties. we should remember that cryptography deals with large integers. Example, the following shows the application of the properties. 1. 17,23,345 mod 11 plus 21,24,945 mod 11 is equal to 8 plus 9 mod 11, which is equal to 6. The above calculation is same for the next two examples. 2. 17,23,345 minus 21,24,945 mod 16 is equal to 8 minus 9 mod 11, which is equal to 10. 3. 17,23,345 into 21,24,945 mod 16 is equal to 8 into 9 mod 11 is equal to 6. Inverses. In this video, we are going to see about inverses. In modular arithmetic, we frequently need to find the inverse of a number relative to operation. We are generally glance for an additive inverse relative to an addition operation or a multiplicative inverse relative to a multiplication operation. Additive inverse. In Zn, two numbers a and b are additive inverses of each other if a plus b is equal to 0 mod n. In Zn, the additive inverse of a can be calculated as b is equal to n minus a. For example, the additive inverse of 4 in Z10 is 10 minus 4, which is equal to 6. In modular arithmetic, each integer has an additive inverse. The sum of an integer and its additive inverse is congruent to 0 modulo n. Multiplicative inverse. In Zn, two numbers a and b are the multiplicative inverses of each other if a into b is equal to 1 mod n. For example, if the modulus is 10, then the multiplicative inverse of 3 is 7. In other words, we have 3 into 7 mod 10 is equal to 1. In modular arithmetic, an integer may or may not have a multiplicative inverse. When it does, the product of the integer and its multiplicative inverse is congruent to 1 modulo n. This can be proved that a have multiplicative inverse in Zn if and only if GCD of n a is equal to 1. In this case, a and n are said to be relatively prime. Example 1. Find the multiplicative inverse of 8 in Z10. Solution. There is no multiplicative inverse because GCD of 10, 8 is equal to 2, not equal to 1. In other words, we cannot find any number between 0 and 9 such that when multiplied by 8, the result is congruent to 1. Example 2. Find all multiplicative inverses in Z10. Solution. There are only 3 pairs, 1, 1, 3, 7 and 9, 9. The numbers 0, 2, 4, 5, 6 and 8 do not have a multiplicative inverse. Example 3. Find all multiplicative inverse pairs in Z11. Solution. We have 7 pairs, 1, 1, 2, 6, 3, 4, 5, 9, 7, 8, 9, 9 and 10, 10. The extended Euclidean algorithm finds the multiplicative inverses of b in Zn when n and b are given and GCD of nb is equal to 1. The multiplicative inverse of b is the value of t after being mapped to Zn. We find the multiplicative inverse of a number using the extended Euclidean algorithm. Example 4. Find the multiplicative inverse of 11 in Z26. Solution. We used this table similar to the one used before with R1 is equal to 26 and R2 is equal to 11. We concentrate the value of t. The GCD of 2611 is 1, which means that the multiplicative inverse of 11 exists. The extended Euclidean algorithm gives t1 is equal to -7. The multiplicative inverse is -7 mod 26 is equal to 19. In other words, 11 and 19 are multiplicative inverse in Z26. We can see that 11 into 19 mod 26 is equal to 209 mod 26 is equal to 1. Addition and multiplication tables. In this video, we are going to see about addition and multiplication tables. Addition and multiplication tables. Two tables for addition and multiplication. In the addition table, every integer has additive inverse. The inverse pairs can be found when the result of addition is 0. We have 0, 0, 1, 9, 2, 8, 3, 7, 4, 6 and 5, 5. In the multiplication table, we enclose only 3 multiplicative pairs, that is 1, 1, 3, 7 and 9, 9. The pairs can be found whenever the result of multiplication is 1. Both tables are symmetric with respect to the diagonal of elements that moves from the top left to the bottom right, revealing the commutative property for addition and multiplication. A plus b is equal to b plus a and a into b is equal to b into a. The addition table also illustrates that each row or column is a permutation of another row or column. This is not true for the multiplication table. Different sets for addition and multiplication. In this video, we are going to see about different sets for addition and multiplication. In cryptography, we frequently work with inverses. If sender uses an integer as the encryption key, the receiver uses the inverse of that integer as the decryption key. If operation, that is encryption or decryption algorithm, is addition, Zn can be used as the set of probable keys because each integer in this set has an additive inverse. On the other hand, if the operation, that is encryption or decryption algorithm, is multiplication, Zn cannot be the set of probable keys because only some members of this set contain a multiplicative inverse. We need another set. The new set, which is a subset of Zn, includes only integers in Zn that have a unique multiplicative inverse. This set is called Zn group. Few occurrences of two sets. Note that Zn group can be made from multiplication tables. Each member of Zn has an additive inverse, but only some members contain a multiplicative inverse. Each member of Zn group has a multiplicative inverse, but only some members have an additive inverse. We need to use Zn when additive inverses are needed. We need to use Zn group when multiplicative inverses are needed. Two more sets. In this video, we are going to see about two more sets. Cryptography frequently exercises two more sets, ZP and ZP group. Modulus in this two set is a prime number. Prime number have only two divisors, integer 1 and itself. The set ZP is similar as Zn except that n is a prime. ZP have all integers from 0 to p minus 1. Each member in ZP have additive inverse. Each member except 0 has a multiplicative inverse. The set ZP group is similar as Zn group except that n is a prime. ZP group have all integers from 1 to p minus 1. Each member in ZP group have additive and multiplicative inverse. ZP group is very good applicant when we require a set that hold up both additive and multiplicative inverse. The following shows these two sets when p is equal to 13. Z13 is equal to set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Z13 group is equal to set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Definition of Euclidean algorithm. In this video, we are going to see about the definition of Euclidean algorithm. Euclid's algorithm is a technique for calculating the greatest common divisor GCD of two usually positive integers known as the greatest common factor GCF or highest common factor HCF. The two integers are relatively prime if their only common positive integer is 1. Euclid's algorithm begins with a pair of positive integers and creates a new pair that contains the smaller number and difference between the larger and smaller numbers. The procedure recurs until the numbers in the pair are equal. Then, the number is the greatest common divisor of the original pair of integers. The major principle is that the GCD does not alter if the smaller number is subtracted from the larger number. For example, the GCD of 252 and 105 is accurately the GCD of 147 equal to 252 minus 105 and 105. So, the larger of the two numbers is reduced. Recurring this process provides successively smaller numbers, so this recurrence will necessarily stop earlier or later. When the numbers are equal, if the process tries once more, one of the numbers will become 0. Greatest common divisor. In this video, we are going to see about greatest common divisor. The greatest common divisor GCD, also called as greatest common factor GCF, highest common factor HCF of two or more integers, at least one of which is not 0, is the largest positive integer that divides the numbers without a remainder. For example, the GCD of 8 and 12 is 4. A non-zero b is defined to be divisor of a if a is equal to mb for some m where a, b and m are integers. We can use the notation GCD of a, b to mean the greatest common divisor of a and b. The greatest common divisor of a and b is the largest integer that divides both a and b. We also define GCD of 0, 0 is equal to 0. The positive integer is said to be the greatest common divisor of a and b, and if c is a divisor of a and b, any divisor of a and b is a divisor of c. An equivalent definition is the following. GCD of a, b is equal to max k such that k divided by a and k divided by b, because we need that greatest common divisor be positive. GCD of a, b is equal to GCD of a, minus b is equal to GCD of minus a, b is equal to GCD of minus a, minus b. In general, GCD of a, b is equal to GCD of modulus A, modulus B. GCD of 60, 24 is equal to GCD of 60, minus 24 is equal to 12. Here, all non-zero integers divide 0. We have GCD of A, 0 is equal to modulus of A. The two integers a and b are relatively prime if their only common positive integer factor is 1. This is equivalent to saying that a and b are relatively prime if GCD of a, b is equal to 1. 8 and 15 are relatively prime because the positive divisors of 8 are 1, 2, 4 and 8, and the positive divisors of 15 are 1, 3, 5 and 15. So, 1 is the only integer on both the lists. Finding the greatest common divisor. In this video, we are going to see about finding the greatest common divisor. We describe Euclid algorithm for easily finding the greatest common divisor of two integers. Suppose we have integers a, b such that d is equal to GCD of a, b, because GCD of modulus a, modulus b is equal to GCD of a, b. There is no harm in assuming a is greater than or equal to b is greater than 0. Now dividing a by b and applying the division algorithm, we can state a is equal to q1b plus r1, 0 lesser than or equal to r1 lesser than b. If r1 is equal to 0, then b divided by a and d is equal to GCD of ab is equal to b. But if r1 is not equal to 0, we can state that d divided by r1. This is because of the properties of divisibility. The relations d divided by a and d divided by b together imply that d divided by a minus q1 into b, which is the same as d by r1. Let the equation 1 a is equal to q1b plus r1, 0 lesser than or equal to r1 lesser than b. Assume that r1 is not equal to 0 because b is greater than r1. We can divide b by r1 and apply the division algorithm. b is equal to q2 into r1 plus r2, where 0 is less than or equal to r2 lesser than r1. Previously, if r2 is equal to 0, then d is equal to r1, and if r2 is not equal to 0, then d is equal to GCD of r1, r2. The division algorithm procedure keep on until a few zero remainder appears at the n plus 1th stage, where Rn minus 1 is divided by Rn. The result is the last division in the above table. Rn divides a and b. Next to the last division, illustrate that Rn divides Rn minus 2 because it divides both terms on the right. Consecutively, one notices that Rn divides all Ri and finally a and b. It remains to illustrate that Rn is the biggest divisor that divides a and b. If we take any arbitrary integer that divides a and b, it should divide R1 as explained before. Now see the example with relatively large numbers to see the power of this algorithm. In this example, we start by dividing 1160718174 by 316258250, which gives 3 with remainder of 211943424. This procedure continues up to we get a remainder of 0, yielding a result of 1078. It could be useful in what follows to recast the above calculation in tabular structure. In every step of the iteration, we have Ri minus 2 is equal to Qi Ri minus 1 plus Ri, where Ri minus 2 is the dividend Ri minus 1 is the divisor, Qi is the quotient, and Ri the remainder. Introduction to finite fields of the form GF of P. In this video, we are going to see about introduction to finite fields of the form GF of P. Finite fields participate vital role in a lot of crypto algorithms. It is shown that the order of a finite field should be a power of a prime p power n, where n is a positive integer. Prime is an integer whose only positive integer factors are itself and 1. The finite field of order p power n is generally represented by GF of p power n. GF stands for Galiot's field, in honor of the French mathematician Évariste Galiot. The two special case for our purposes: for n is equal to 1, we have the finite field GF of P. This finite field has a different structure than that for finite fields with n greater than 1. Finite fields of order P. For a given prime P, GF of P is defined as the set Zp is equal to 0, 1 and so on up to p minus 1 of integers together with arithmetic operations modulo P. For such prime numbers holds M7 multiplicative inverse axiom. We observed that any integer in Zn has a multiplicative inverse if and only if that integer is relatively prime to n, and therefore there exists a multiplicative inverse for all of the non-zero integers in Zn. Because elements W of Zp are relatively prime to P, if we multiply all the elements of Zp by W, the resulting residues are all of elements Zp permuted. Multiplicative inverse, W inverse. For each W belongs to Zp, W is not equal to 0, there exists a Z belongs to Zp such that W into Z is equal to 1 mod P. Thus, exactly one of the residues has the value 1, respective multiplier is just the inverse element for W, designated W inverse. Therefore, Zp is in fact a finite field. Furthermore, if A into B is equal to A into C mod n, then B is equal to C mod n if A is relatively prime to n. This equation is consistent with the existence of a multiplicative inverse and can be rewritten without the condition. If A into B is equal to A into C mod P, then B is equal to C mod P. 1.3. Multiplying both sides of equation 1.3 by the multiplicative inverse of A, we have A inverse into A into B is equal to A inverse into A into C mod P. B is equal to C mod P. The above tables illustrates arithmetic operations in GF of 7. It is a field of order 7 using modular arithmetic modulo 7. It satisfies all of the properties of a field. Finding the multiplicative inverse in GF of P. In this video, we are going to see about finding the multiplicative inverse in GF of P. Finding the multiplicative inverse in GF of P. It is simple to discover the multiplicative inverse of an element in GF of P for small values of P. Construct a multiplication table and the preferred result can be read directly. However, for large values of P, this approach is not practical. The following table illustrates arithmetic in GF of 7. If A and B are relatively prime, then B have a multiplicative inverse modulo A. That is, if GCD of A, B is equal to 1, then B have a multiplicative inverse modulo A. That is, for positive integer B is less than A, there exists A B inverse is less than A such that B inverse is equal to 1 mod A. If A is a prime number and B is less than A, then clearly A and B are relatively prime and have a greatest common divisor of 1. We now illustrate that we can easily calculate B inverse using the extended Euclidean algorithm. We do again here the extended Euclidean algorithm. Ax plus by is equal to d is equal to GCD of A, B. Now, if GCD of A, B is equal to 1, then we have Ax plus by is equal to 1. Using the fundamental equalities of modular arithmetic, we can say Ax mod A plus by mod A is equal to 1 mod A 0 plus by mod A is equal to 1. But if by mod A is equal to 1, then y is equal to B inverse. Therefore, applying the extended Euclidean algorithm to this equation, Ax plus by is equal to d is equal to GCD of A, B, and acquires the value of the multiplicative inverse of b if GCD of A, B is equal to 1. Consider this extended Euclidean algorithm example. Result: d is equal to 1, x is equal to minus 111, y is equal to 355. Here we include a is equal to 1759, which is a prime number, and b is equal to 550. The solution of the equation 1759x plus 550y is equal to d acquires a value of y is equal to 355. Thus, B inverse is equal to 355. To confirm, we compute 550 into 355 mod 1759 is equal to 1. Usually, the extended Euclidean algorithm can be used to discover a multiplicative inverse in Zn for any n. If we apply the extended Euclidean algorithm to the equation nx plus by is equal to d, and the algorithm yields d is equal to 1, then y is equal to B inverse in Zn. Introduction to Polynomial Arithmetic. In this video, we are going to see about Introduction to Polynomial Arithmetic. Polynomial arithmetic is a division of algebra dealing with some properties of polynomials which share strong analogies with properties of number theory relative to integers. We are concerned with polynomials in a single variable x, and we can differentiate three classes of polynomial arithmetic. Normal polynomial arithmetic using the basic rules of algebra. Polynomial arithmetic, in which the arithmetic on the coefficients is executing modulo p, that is, the coefficients are in GF of p. In polynomial arithmetic, which the coefficients are in GF of p and the polynomials are defined modulo a polynomial m of x, whose highest power is some integer n. Ordinary polynomial arithmetic. A polynomial of degree n, integer n is greater than or equal to 0, is an expression of the form f of x is equal to an x power n plus an minus 1 x power n minus 1 plus and so on up to plus a1x plus a0 is equal to sigma I is equal to 0 to n ai x power I. For some non-negative integer n, and where the coefficients a0, a1 and so on up to an are drawn from some designated set S. S is called a coefficient set. When an is not equal to 0, we have a polynomial of degree n. A 0th degree polynomial is called a constant polynomial. An nth degree polynomial is said to be a monic polynomial if an is equal to 1. Polynomial arithmetic deals with the addition, subtraction, multiplication, and division of polynomials. Addition and subtraction are performed by adding or subtracting equivalent coefficients. Thus, if f of x is equal to sigma I is equal to 0 to n ai x power I, g of x is equal to sigma I is equal to 0 to m bi x power I, n is greater than or equal to m. Then addition is defined as f of x plus g of x is equal to sigma I is equal to 0 to m ai plus bi into x power I plus sigma I is equal to m plus 1 to n ai x power I. And multiplication is defined as f of x into g of x is equal to sigma I is equal to 0 to n plus 1 ci x power I, where ck is equal to a0 bk plus a1 bk minus 1 plus and so on up to ak minus 1 b1 plus ak b0. In the last formula, we consider ai as 0 for I is greater than n and bi as 0 for I is greater than m. Note that the degree of the product is equivalent to the sum of the degrees of the two polynomials. For example, let f of x is equal to x cubed plus x square plus 2 and g of x is equal to x square minus x plus 1, where s is the set of integers. Then f of x plus g of x is equal to x cubed plus 2x square minus x plus 3. f of x minus g of x is equal to x cubed plus x plus 1. f of x into g of x is equal to x power 5 plus 3x square minus 2x plus 2. Polynomial arithmetic with coefficients in ZP. In this video, we are going to see about polynomial arithmetic with coefficients in ZP. Polynomials in which the coefficients are elements of some field f, we refer to this as a polynomial over the field f. It is simple to illustrate that the set of such polynomials is a ring called as a polynomial ring. If the polynomial arithmetic is performed in a field, then division is possible. Note this does not mean that exact division is possible. Consider that given polynomials f of x of degree n and g of x of degree m. N is greater than m. If we divide f of x by g of x, we get a quotient q of x and a remainder r of x that obey the relationship f of x is equal to q of x into g of x plus r of x with polynomial degrees. Degree f of x is equal to n, degree g of x is equal to m, degree q of x is equal to n minus m, degree r of x is equal to m minus 1. A polynomial f of x over a field f is called irreducible if and only if f of x cannot be expressed as a product of two polynomials, both over f and both of degree lower than that of f of x. By analogy to integers, an irreducible polynomial is also called a prime polynomial. The examples of polynomial arithmetic over gf of 2. Finding the greatest common divisor. In this video, we are going to see about finding the greatest common divisor. The polynomial c of x is said to be the greatest common divisor of a of x and b of x if the following are true. C of x divides both a of x and b of x. Any divisor of a of x and b of x is a divisor of c of x. GCD of a of x, b of x is the polynomial of maximum degree that divides both a of x and b of x. GCD A of x, B of x is equal to GCD of B of x, A of x mod B of x. The above equation can be used repetitively to determine the greatest common divisor. Compare the following scheme to the definition of the Euclidean algorithm for integers. In every iteration, we have d of x is equal to GCD of Ri plus 1 of x, Ri of x, until finally d of x is equal to GCD of Rn of x, 0 is equal to Rn of x. We can identify the greatest common divisor of two integers by repetitive application of the division algorithm. This is the Euclidean algorithm for polynomials. The algorithm assumes that the degree of a of x is greater than the degree of b of x. Introduction to finite fields of the form gf of 2n. In this video, we are going to see about introduction to finite fields of the form gf of 2n. Polynomials in p power n with n greater than 1, operations modulo p power n do not supply a field. In this part, we illustrate that structure satisfies the axioms for a field in a set with p power n elements and concentrate on gf of 2 power n. Motivation is virtually have all encryption algorithms, both symmetric and public key, involve arithmetic operations on integers with divisions. For efficiency, integers that fit exactly into a given number of bits with no wasted bit patterns, integers in the range 0 through 2 power n minus 1, fitting into an n-bit word, Z256 versus Z251. The finite fields of the form gf of 2 power n are attractive for cryptographic algorithms. A set consisting of elements with the definition of addition and multiplication over the set that define a field. Assign a unique integer in the range 0 through 2 power n minus 1 to each element of the set. Keep in mind that we will not use modular arithmetic, as we have seen that this does not result in a field. Instead, we will show how polynomial arithmetic provides a mean for constructing the desired field. Modular polynomial arithmetic. In this video, we are going to see about modular polynomial arithmetic. Consider the set S of all polynomials of degree n-1 or less over the field. Then each polynomial has the form f of x is equal to a n-1 into x power n-1 plus a n-2 into x power n-2 and so on up to a1 into x plus a0 is equal to summation of I is equal to 0 to n-1 ai into x power I, where each ai takes on a value in the set 0, 1 and so on up to p-1. There are a total of p power n different polynomials in S. Arithmetic follows the ordinary rules of polynomial arithmetic using the basic rules of algebra with the following two refinements. Arithmetic on the coefficients is performed modulo p using the rules of arithmetic for the finite field Zp. If a multiplication result is a polynomial of degree greater than n-1, then the polynomial is reduced modulo some irreducible polynomial m of x of degree n. That is, we divide by m of x and keep the remainder. For a polynomial f of x, the remainder is expressed as r of s is equal to f of x mod m of x. The set of residues modulo m of x, an nth degree polynomial, contains of p power n elements. Each of the elements is denoted by one of the p power n polynomials of degree m less than n. This table illustrates a polynomial arithmetic modulo addition for x cube plus x plus 1. This table illustrates a polynomial arithmetic modulo multiplication for x cubed plus x plus 1. Finding the multiplicative inverse. In this video, we are going to see about finding the multiplicative inverse. The Euclidean algorithm used to find the greatest common divisor of two polynomials. The extended Euclidean algorithm used to find the multiplicative inverse of a polynomial. Especially, the algorithm will find the multiplicative inverse of b of x modulo a of x if the degree of b of x is less than the degree of a of x, and GCD a of x comma b of x is equal to 1. If a of x is an irreducible polynomial, then it has no factor other than itself or 1. So that GCD of a of x comma b of x is equal to 1. We solve the following equation for the values v of x, w of x and d of x, where d of x is equal to GCD of a of x, b of x. A of x into v of x plus b of x into w of x is equal to d of x. If d of x is equal to 1, then w of x is a multiplicative inverse of b of x modulo a of x. The algorithm follows extended Euclid m of x, b of x. a1 of x, a2 of x, a3 of x is equal to 1, 0 m of x. b1 of x plus b2 of x, b3 of x is equal to 0, 1 b of x. If b3 of x is equal to 0, return a3 of x is equal to GCD of m of x, b of x, no inverse. If b3 of x is equal to 1, return b3 of x is equal to GCD of m of x, b of x. b2 of x is equal to b of x inverse mod m of x. q of x is equal to quotient of a3 of x divided by b3 of x. t1 of x, t2 of x, t3 of x is equal to a1 of x minus q b1 of x, a2 of x minus q b2 of x, a3 of x minus q b3 of x. a1 of x, a2 of x, a3 of x is equal to b1 of x, b2 of x, b3 of x. b1 of x, b2 of x, b3 of x is equal to t1 of x, t2 of x, t3 of x. Go to 2. The calculation of the multiplicative inverse of x power 7 plus x plus 1 mod x power 8 plus x power 4 plus x cubed plus x plus 1. The result is that x power 7 plus x plus 1 inverse is equal to x power 7. That is, x power 7 plus x plus 1 into x power 7 is equal to 1 mod x power 8 plus x power 4 plus x cubed plus x plus 1. Using a generator. In this video, we are going to see about using a generator. A corresponding method for defining a finite field of the form gf of 2 power n using the same irreducible polynomial is sometimes more convenient. A generator G of a finite field f of order q contains q elements is an element whose first q minus 1 powers generate all the non-zero elements of f. That is, the elements of f consist of 0, g power 0, g power 1 and so on up to g power q minus 2. Consider a field f defined by a polynomial f of x. An element b contained in f is called a root of the polynomial if f of b is equal to 0. Finally, it can be shown that a root g of an irreducible polynomial is the generator of the finite field defined on that polynomial. The below table illustrates the generator for df of 2 power 3 using x cubed plus x plus 1.